Welcome to my digital learning resource on thermodynamics. So these are some important definitions. It's important to differentiate between temperature and heat because they're two different things. Temperature is the average kinetic energy of the particles in a substance, so how fast the particles are moving. And heat is the transfer of energy from an object of higher kinetic energy to an object with lower kinetic energy. So the heat is transferred from one object to the surroundings, and that's the transfer. That's what heat is. And thermal equilibrium is the point at which the transfer stops, because both objects have the same kinetic energy or temperature. Here's this ball of hot nickel, and you see it's melting through the ice. And that's because they're hotter and it's transferring the energy. And when it stops, that's when it's reached thermal equilibrium, so the temperatures are the same. That's what you see right here. And then, as we see, the kinetic energy from the nickel atoms is used to break the water molecules. And then it will break, when water is in the liquid state, it's 20% of the bonds are broken, and when it's a gas, all of the bonds are broken, and the solid, all of the bonds are intact. And it stopped falling through because it reached thermal equilibrium. They were the same temperature. So the physical states of water, they're ice, all of the bonds are formed, and these are molecular covalent bonds, and the water has a low melting point because the bonds in molecular covalent bonds, the bonds within the molecules are strong, but between the molecules it's weak, so they fall apart easily, which is why water is liquid at room temperature, and then all of the molecules break apart when it's in its gaseous state. Let's dig deeper into what heat is. Heat can be calculated, and it's a certain number. Q stands for the transfer of energy, so heat, and it's in joules or calories. It's equal to mass in grams times a specific heat capacity, which is the amount of energy required to raise 1 gram of a substance 1 degree Celsius, and times delta T, which is the change in temperature. And this is used to determine the amount of energy transferred in joules or calories. In calorimetry, measuring heat flow usually through watching the temperature of the surroundings change. As you see in this picture here, there's metal in the hot water, so the water and the metal are at the same temperature. And when you put that hot metal into an insulated container with water at room temperature in it, the heat will transfer out of the metal and into the water. So when it says Q system equals the negative Q surrounding, it's the opposite for this. So the system is losing its energy, and the system is losing its temperature and its energy, and the surroundings is gaining it. So it's negative Q sys equals positive Q surroundings. In this lab with the metal, here's some raw data, and we use this to determine which metal it was. And by comparing the specific heat capacity we determined from the calculations to the one on the internet or in the textbook. And the C for water is 4.184. And since, as you can see, the numbers aren't quite the same, but since the metal was less heavy than the rest of them and a light silver color, I deduced that it was aluminum. As I said before, the system was losing its energy, and that is exothermic. The energy is leaving the system and going into the surroundings so that they can reach thermal equilibrium. The ice temperature cannot be lowering and melting at the same time. This latent heat of fusion and latent heat of vaporization is basically the phase change, and that's how physicists say it. Endothermic is the exact opposite. So when the heat's going into the system, the kinetic energy is raised, the particles speed up, and the temperatures increase, or the intermolecular forces are breaking, so there's a phase change. You can see here that while the temperature is rising in water, it goes to almost boiling, and then it starts boiling, and that's why the temperature no longer increases, and the phase is changing, so the temperature stays the same. Let's move on to enthalpy. So enthalpy is the heat absorbed or released when the potential energy of a system is raised or lowered due to bonds breaking or forming in intermolecular forces. So in an endothermic reaction, the delta H is positive, and in exothermic, it's negative. So this heat is leaving with the system, so the enthalpy is negative. And so the temperature rises in exothermic in the surrounding, and the temperature decreases when it's in the surrounding when it's endothermic. The big truth here is that the energy required to break bonds is less than the energy released when bonds form. So in Hess's law, we can think about it as product compounds are forming when the reactants are unforming. So because there's more energy released when the bonds form, in a sense, you gain energy when a reaction happens, because more energy is released when the bonds form than when the reactants bonds are breaking. This delta H degrees F is the standard enthalpy of formation, is what that stands for. It's the energy released when a compound forms from its elements. This fancy math is basically, the delta H is basically the sum of the products minus the sum of the reactants. And in the case of this reaction below, the delta H is positive, and these numerical values are found in the magical appendix G, or in the magic of the internet. Yeah, thank you for watching. Goodbye.
It's so hard to believe, but it's all coming back to